So far we've seen that neural networks can be very effective, but the actual weights themselves that we use to classify what we've looked at so far, they're sort of appearing by magic. So this video is going to give you an overview of the concepts that are going on in order to create these weights. So remember that the key difference between neural networks and the traditional machine learning tools are that the features that we are working with are going to be automatically calculated by the network rather than it being something that is produced by humans. This video is trying to explain how that process comes about. So far we've only looked at what's called the forward pass, where we go from the input to the output. When we want to update the network, we have to go back through it. Essentially what is going to happen is we'll have all of these weights in both of these layers, or more layers if we're working with a deeper neural network, and we're going to backpropagate through the network. So we start off with all of these weights being completely random, but between 0 and 1. And then we're going to go forward through the network one time. And then we're going to see where the errors are and try and work out the best ways that we can reduce those errors. So that's where we go backwards and we come back to the input. And that's going to happen hundreds of times, thousands of times, hundreds of thousands of times, depending on how long you want to train your model, depending on how big your model is, how difficult it is to train, or how big your data set is. So this process is going to rely on some slightly more advanced mathematics. When we come to coding this, it's all done automatically. So because this is more of a practical module rather than being a really deep theoretical module, I am going to skip over a lot of the maths. You can look into this further for your mathematical background assessment if you would like. But yeah, I know a lot of you won't have seen partial differentiation before, and this technique, this algorithm, depends fully on partial differentiation. I'm not going to go into that. I'm going to give you an idea of what's going on. So for this network, we've got 3 classes. So this is y1, y2, and y3. And let's say we've just got one input vector that we care about. Okay, and it's of class 1. So the result that we should get is 1, 0, 0. And we start off randomly and we get very lucky and we get a pretty good starting guess. So these weights that we start off with are pretty lucky. We get 0.5, 0.5, 0. Okay, so we're doing reasonably well already. One of the ways that we could look to do something about this is by looking at all of these weights individually. So remember, originally this was W1, 1, because this is the input 1, so this is X1 and this is H1. So I'm just going to put another 1 here to say that this is in the first layer, and then this one is in the second layer. So this would be W1, 1, 2. Actually, maybe that's not too important. I'll just do it a little bit simpler. Let's call this one WA. And we're just going to focus on WA for now. So if we change WA a little bit, then let's say instead of WA, which we can say again, this was its initial like random instantiation was 0. So we're going to change this a tiny little bit, and we're going to take it from 0 to 0.01. What's going to happen now? We're going to get this calculation is going to be slightly different. So this is going to change a very little bit. This might become 0. Remember, so we're going to do something which normalizes this output. So if this becomes 0.51, then this one will become 0.49, or it might even become 0.48, and then this one will become 0.01. Essentially, when we make some tiny little change to one of these weights, it's going to have a little bit of an impact on the final result. So when we start off with each of these weights, what we're trying to do is work out for every single weight that we've got for this W1 and for this W2, we want to evaluate every single one of those weights and work out which direction we need to push, like to actually nudge those weights just a tiny little bit so that we get a slightly better performance. And we're going to do that over and over and over again. And what we do for this, the way that we do that, rather than doing that process that I've just described for each weight individually, we're instead going to work back through the network with a new input. So instead of, if I go back to my original outcome, so if we have 0.5, 0.50, and we should have 1, 0, 0, we're just going to take the difference between these two vectors, which is going to be minus 0.5, 0.50. We're going to take that difference, and if we're doing L1 difference, then we're going to want to do the modulus of these. So this then becomes 0.5. This is explained in the vectors, matrices, and tensors video. We take this and we work backwards through. So we take this one, and this is like the input to a neural network, but it's going backwards. So we use the exact same weights as before, but we're going to do partial differentiation to get new values for each of these. You just need to remember that it's the difference in the error that we have here. So this vector is going to come from something called a loss function, which I'll talk about in lecture 5. So this gets quite complicated. If you're interested in backpropagation, if you're interested in maths and want to learn more about this, I do want to really highly recommend this paper, Backpropagation and the Brain, which was released last year in Nature, which is just in this bottom corner. And this goes into a little bit more detail. Already, this is still a reasonably simplistic explanation of backpropagation, but the maths and the notation's already getting a little bit complicated, and I don't want to get into all of the detail here. The important thing to note basically is that this is what's going on, and because this relies on differentiation, when you develop a neural network, any function within that neural network has to be differentiable. Otherwise, this backpropagation process won't work, which means that the whole system will fall down at the first hurdle. So Because this is a practical module, not a theoretical module, I'm not going to dive into the maths any deeper than this. You don't need to know it anymore to develop really, really strong neural networks or deep learning mechanisms or deep learning frameworks, because all of this is done automatically by Keras, by TensorFlow, by PyTorch, whichever deep learning library you want to use. It's all done automatically, so we don't need to know this in detail. But I do want to let you know what the sort of concept is in case you are interested to explore further. Another thing that I just want to mention, this backpropagation in the brain paper, if you're interested in the possible similarity between what's going on in neural networks and what's going on in the brain, this is a fantastic paper to try and explore to develop your understanding. So it's not true to say that what's going on within neural networks and what's going on in the brain is the same. Neural networks are loosely inspired by that process, but this paper tries to explore how the brain might do something similar to backpropagation, which is really fascinating. So I'd encourage you to check that out if you're interested.